Hey everybody, this is obviously a video going through section 3.5 concerning improper integrals. The context surrounding me making this video right here, right now, is pretty much all because of a pretty crazy moment in our history. Today is actually March 20th, 2020, which makes it day 5 that school has been off because of the virus. So Friday, March 20th, that we've been in quarantine. At this point, school is off for at least another week, but I don't think anyone's going to be surprised if that gets extended, and maybe even the rest of the year gets called off. I mean, at least that's what I'm trying to prepare for here. Obviously, right now I'm teaching an AP Calc BC course. I have 8, wonderful students in that class, and in case we have to start teaching from home, and the students have to start learning from home and doing some sort of assignments from home, then I'm gonna try to get back on this, and making any calc videos that I do not already have prepared, or if the whole rest of the year gets called off and it's all kind of a wash, whatever they got in their immediate future with college and or maybe just their own curiosity about what else we were going to learn in Calc BC class. So let's get into 3.5 here. Funny enough, the very last day, like literally 1 week ago, last Friday, we actually started this section already. I don't know if they remember. I think we did most of this section, but I'm just going to run through the whole thing again. So we have the whole lesson, the whole the whole group of notes kind of complete on this video. The music you hear in the background is from the movie Cloud Atlas, which, some weird irony, is a movie starring Tom Hanks. And I didn't even realize this. Like I kind of picked this song because it was just a nice thing to have in the background, and then I realized, oh my gosh, like Tom Hanks is in this movie, and Tom Hanks was maybe the very first big time celebrity that kind of came out and said that he had contracted the coronavirus. But anyway, so improper integrals. This is the final section that I do in this Unit 3, which is about integration techniques and L'Hopital's rule and improper integrals. So far in this unit, we've done integration by parts, and then we saw how a lot of integration by parts integrals, problems can be done with like this integration by tables. And you're gonna hopefully remember that integration by tables is kind of like a cool, like fast tracking, of integration by parts. It's essentially integration by parts, but it's much quicker and much more neat and tidy. But while I'm talking about that, just kind of remember that you can't really use integration by tables on all integration by parts examples. You can't really use it when there's a natural log involved and and how you're letting u equal the natural log, because you're going to be because you're going to be taking the derivative of natural log and all that business. And so integration by tables won't work when there's the natural log thing, and integration by tables will also not work when you have, like, let's say an exponential, like you have e to the x or something, some type of e to the whatever function involved, as well as like a trig function. So let's say, just for example, it was like the integral of e to the x times the sine of x dx, and you were going to need to apply integration by parts to that. But that special kind of problem will also not really work with integration by tables. But so getting back on track, we had integration by parts, integration by tables, and then in section 3 we learned the whole like partial fraction algebra trick that sometimes you have to do when you're doing an integral. Then section 4 we talked about L'Hopital's rule, which seemed like a big change of gears, because it was really about limits. Like, we weren't really integrating, we were taking limits. So it was almost like, how does this belong in this unit? Well, when we're doing improper integrals, you're going to see that limits get involved, and L'Hopital's rule is definitely something that potentially we can use when we're actually doing improper integrals. So it definitely fit a lot better, or it fits a lot better than you might have thought at the time in this whole unit 3. So improper integrals, here we go. It starts off with kind of a quick activity, and it says, consider the infinite region that lies under the curve y equals e to the negative x over 2 power in the first quadrant. So the area just in the first quadrant underneath this curve. And so here's kind of like a Desmos picture of that function, and so we're just kind of talking about this area just in the first quadrant here under the curve. And because of the way the curve kind of goes off with its end behavior off to the right, you would think that this area is infinite. Well, you might think. How's that for foreshadowing, or sort of like spoilers? Obviously this is kind of leading to the fact that it isn't. You might think this region is infinite, but when we actually go ahead and analyze this, okay, with so the area from 0 to b, okay, and b is going to be some x value. Like if we went from 0 to 1, we would have this certain region of area. If we went from 0 to 3, we would have even more, okay? But, this infinite region, we're going from 0 to essentially, infinity. So we're going to set this integral up and say 0 to b, and we're going to integrate the function. And when we do that, and we're doing this by hand now, so kind of a review of integration by hand, where you're not really using technology, you're kind of going to be plugging in b to the integral and plugging in 0 and subtracting those two results. So again, this is going back to like integrating definite integrals by hand without doing like the math 9 thing, the function integrate on our calculators. So we're gonna take this now, which cleans up, okay, like that, and maybe even by now you've realized what we're about to do, to pretty much think about like what's the infinite area going to be. We're going to take the limit and let b approach infinity and see what happens there, okay? So if we take the limit of this, and as b approaches infinity, this exponent kind of approaches, see how there's a negative there? It approaches like negative infinity, you know? It's almost like 1 over e to the positive infinity, which that approaches 0. So again, this part right here, if b approaches infinity, this whole e to the that, you know, like approaches 0, because it's like 1 over something that's getting bigger and bigger and bigger and bigger. It's kind of like having 1 over 2 become 1 over 5, which becomes 1 over 10, which becomes 1 over 50. You know, that's approaching 0. So this whole part over here, this whole like term, gets wiped out, and what's left over is just 2. So again, kind of summarizing this, it turns out that this infinite area is actually equal to 2, because we kind of, I think, ended up in this situation where you know, this area keeps on getting added to, like you're always adding more area, but what you're adding is getting smaller and smaller and smaller. So we're always approaching 2, right? And you might as well say 2, because you're never going to reach a total area of 2, and since you're going to get like infinitely closer to that, we're going to get as close as we really want to 2. We're getting closer and closer, literally forever. We might as well say the area is 2. Alright, so now some official definitions, like what really is an improper integral. I mean, it's the title of the section here. So what is an improper integral? An improper integral, integrals with infinite limits of integration. So integrals with infinite limits of integration are improper integrals. And so we have all this craziness. What's in blue, what's in red, what's in purple. And I'm probably going to end up moving on here before you have time to write all this down. So, I mean, as always, with any video I always make, or ever make, you can always feel free to pause it, or go back and watch certain parts again, or just to give yourself time to write everything down. But we could have like a limit where we're going from some number to infinity, and this is what we're going to be kind of doing. And we could have, or we could have a limit where we go from negative infinity to some number, and again we just do a limit thing. And these limits, or sorry, these integrals, my bad. These integrals converge, okay, which means they'll have an answer, if the limit is finite. And if the limit fails to exist, or it's probably better to say, we actually talked about this in class a week ago, if the limit kind of blows up to infinity or negative infinity. I don't know if fails to exist is the best way to put it. So you might want to make a note of that on your paper. If the limit blows up to infinity or negative infinity, then so does the integral, you know. Because remember, obviously you can have, like, what if you could totally have a function where that happens. I mean, it doesn't take too much creativity to think of, just say like the function x squared, like your typical parabola of y equals x squared. If you were going from 0 to infinity on that integral, then that area, that integral, is obviously just blowing up to infinity. So, I mean, obviously you can totally have, you know, integrals that diverge to infinity. They don't have to converge like this crazy one did. And then we could also, funny enough, have an integral that goes from negative infinity to infinity. And that's where we do this breakup into two separate integrals, where we have one integral go from negative infinity to some c value. Spoiler alert, we're always going to make it 0 because it doesn't matter. So we're just going to make it 0 every time. And the other integral picks up at 0 and goes off to positive infinity. And so we have two separate integrals to deal with. And this integral converges to an answer if both of the new integrals do. So we're going to now see this in action. I know stuff like this, it's hard to understand it and wrap your brain around it. But then we actually do problems, and you'll see how it really works. So here we go. Our first actual example problem, seeing all this in action, and we're starting off with a bang already, from negative infinity to infinity. So we're going to do this breakup into two integrals, and we're going to, like I kind of said, we're going to choose c equals 0. And just really quick, you know how when you integrate something and you get a plus c at the end? That's not the kind of c value we're talking about here. This is a different c value. But so there's our two integrals. We're going to go from negative infinity to 0, and then 0 to infinity. Okay? And next we're going to actually integrate. You know, again, a reminder, pause the video if you need to slow me down, give you a chance to write things down. But at this point now we actually integrate e to the x. And what's the integral of e to the x? Well, that's an easy one. We're going to get e to the x. But first, you know, we got to think of this as a limit. Okay, so I didn't really integrate till down here. So doing the integral of, say, negative infinity to 0, well, we're really going to treat it as a to 0 and let a approach negative infinity. So at this point in time, it's become like we've made it a limit situation, you know. And over here we're going from 0 to b and just letting b approach infinity. So we just kind of rewrote the problem as really a limit, okay, or a couple of limits. And so here's where I've actually integrated, and like I said, you know, a minute ago, the integral of e to the x is obviously just still e to the x. But with a definite integral, now we're going to have to do some plugging in. So we plug in 0 and we plug in a and we subtract those two. And over here we plug in b and we plug in 0 and we subtract those two. And again, pause the video if you need to write this down. But at this point now we actually kind of analyze it and see, like, okay, so what happens when a approaches negative infinity? What happens, and what do we get? And over here, when we let b approach infinity, well, e to the 0 is just 1. Over here, e to the 0 is 1. When we let a approach negative infinity, that's like 1 over e to the a. And like with a approaching positive infinity, you know what I mean? So this right here is going to be approaching 0. If, you know, so kind of a contrast here, right? So going off on a little side note for a second, right? Sidebar. If a was approaching positive infinity, then this whole e to the a would be approaching infinity. You know, actually kind of like this. You know, if b is approaching positive infinity, then this whole e to the b is approaching infinity. But when a is approaching negative infinity, then this entire e to the a is actually approaching 0, because it's like 1 over e to. You just got to remember how that's just how negative exponents work. So that's don't think I'm making this any more complicated than it is. It's really just a matter of what the heck does a negative exponent even mean? Like, how do we deal with negative exponents? That's all this really is, and that's why e to the a is approaching 0. So this approaches 1, so it's really more like 1 minus 0. So what we get here is like 1 minus 0, so 1. And over here we have like basically infinity minus 1, and so really just infinity. And so the final answer here is that this integral diverges. It doesn't converge to an actual answer, it just blows up to infinity. Okay? This next example is really only asking, maybe like the last one is too. No, it's just evaluate if possible. So does this improper integral converge or diverge? And I guess, I don't want to make a big deal about these directions or anything, but if it converges, we're going to be able to see what the answer is. So, this one said evaluate. It was almost like, well, evaluate it if possible, right? You can really only evaluate it if it converges. At least that's what I'm going to say right now. Maybe that's not the right way to say it, but so if it diverges, it diverges. If it converges, then we'll pretty much probably have what it converges to. Anyway, so we're going from 1 to infinity. The first thing is going to be to kind of set it up as a limit. So we're going to really have going from 1 to b. Okay? And if you haven't caught on by now, we're using a as like our default lower limit, and we're using b as our default upper limit. And then if we're doing that c thing, then right. I didn't even use a c variable here, but okay. So we're letting b approach infinity. And so now I think we're ready to what? We're probably going to be integrating now. So what's the integral? What's the integral of 1 over x? That would be the natural log of x. And probably just on a technicality, right? Technically, it would probably be like the natural log of the absolute value of x. But considering all things considered, look, b approaches positive infinity. We're going from 1 to b, and it's always positive. So do we really need the absolute value here on the x? Probably not, because of the whole deal. So we've integrated, and now it's time to plug in b and plug in 1. And now we kind of analyze it. What happens when b approaches infinity? If b approaches infinity, what is the natural log of b approach? Think about that for a second. How about the natural log of 1? What is the natural log of 1? Okay. Maybe you kind of translate that in your head, and you filter that, through your brain as okay, that's really asking. E to what power gets you 1? And of course that's 0. So the natural log of 1 is 0, and the natural log of b approaches infinity. And so this is another example that diverges. All right. Next example problem, next integral is this: the integral from 0 to infinity of 2 all over x squared plus 4x plus 3. So obviously we're going to be writing this as a limit, and we're going to be going from 0 to b and just letting b approach infinity. But thinking ahead here, how would we integrate this? What is the integral of 2 over x squared plus 4x plus 3? And how would you do that? And maybe you're thinking, oh, what about that splitting up into partial fractions that we did earlier in this unit? And that's actually exactly what we're going to be doing. So quick recap of partial fractions. We factor the bottom, and good thing it can factor, right? So we factor the bottom, and that's how we break it up into our 2 fractions. So each factor goes in each denominator. So then we're going to have to solve for whatever a is and whatever b is, and ... we're going to combine these fractions back together with making a common denominator, which is really this. We already kind of know that this is the common denominator, So now when we do that, ... multiplying a by x plus 3 and multiplying b by x plus 1, we get this as really just our numerator. So this right here is really just the numerator only that I'm going to focus on here, okay? So that's what the numerator would be if we kind of combine these fractions back together. And really, the end game here is to figure out how this numerator would match this numerator of just 2. Okay? And so, dot, 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 I'm taking some liberties here, but if you put ax plus bx together, there really is no x term here. So really, it's like having a 0x. So that's why a plus b would end up needing to equal 0, because there is no x term. It's like 0x. Ax plus bx would have to be 0x. And this 3a plus b, that would have to equal 2. And so there's our system of equations, and again, another dot, dot, dot later, that's using maybe the elimination method or something to actually solve for big A and big B. And we end up getting, and again, I'm skipping over some steps, but you end up getting +1 for A and -1 for B. And so that now allows you to rewrite. So all that work and all we've done is rewritten this same exact integral. And so this is really what we're going to be working with, because this we can work with. So, and again, we're going to be doing like the limit thing. So remember, we're really going from 0 to b, and we're taking a limit as b approaches infinity. But I've already integrated here. I've already integrated, so I've kind of made it into a limit problem, and I've also integrated. And remember, the integral of 1 over x plus 1 is just the natural log of x plus 1. Again, absolute value, whatever, okay, but not needed because of all the context. Now, remember, if I can kind of take a breath here for a second, integrating 1 over x plus 1, technically, that's u substitution, right? So just kind of be aware of that, I don't know if actually going through all the steps of u substitution is necessary here, but technically you would let u equal x plus 1. Over here, technically you would let u equal x plus 3. But at the end of the day, after going through those steps, you would just end up with the natural log of x plus 1 and the natural log of x plus 3. As a side note reminder, hope I'm not throwing too much at you, but if this was like a 4x plus 3, then you would see some real impact from doing u substitution. Okay, you would have like a 4 out in front, or a 1/4 or something. I can't remember on the spot. But if you had like a 4x plus 3 here in the denominator, then you might actually want to go through the actual u substitution steps, because there will be some real effect from that. Or if this was like 3x plus 1, then you would actually see some big time results in your answer. But so what happens next? We've integrated, and we have our limits here, b and 0. So now we actually have to like plug in b. So we're going to be plugging in b to these, and then we're going to be like plugging in 0 and subtracting the two results. So all of this was the result of plugging in b. All of this was the result of plugging in 0. Now what's the natural log of 1? That's just 0. The natural log of 3, well, that's just the natural log of 3. Of course, it's like minus, so it's really positive natural log of 3. And what happens over here? If we let b approach infinity, right? We let b approach infinity, we end up basically getting like infinity, the natural log of, that's just infinity, minus infinity. So this is infinity minus infinity. That's one of our indeterminate forms that we can't really work with, and we have to kind of rewrite it. And so that's how I'm going to rewrite that, kind of smushing two logs together, or better technical term is condensing. Condensing them together with the quotient rule of logs. So I kind of smushed these two logs into one with the quotient rule, and now what we have is like infinity over infinity, you know, infinity over infinity. Technically we can do L'Hopital's rule on that, but that's really just going to be 1. And so we have like the natural log of 1 plus the natural log of 3. Of course, the natural log of 1 is really just 0. And so our final answer is that it converges to the natural log of 3. And this over here is kind of like some extra, or, you know, if you couldn't just see that this was L'Hopital's rule, you know, that this was infinity over infinity, or that the limit of this was really just 1. You know, you could have done this super very clever trick of but I'm not really going to address that right here on this video, you know, but it's right there if you want to look at that. It's not necessary. Next example is this integral, right? And so we're going from 1 to infinity. So again, look, thinking ahead, right? Obviously we're going to make this into like a limit and go from 1 to b and let b approach infinity. But looking ahead to actually integrating, how the heck are we going to integrate when it comes time? When the time comes, how are we going to integrate x e to the negative x? Well, that's going to be integration by parts, or better yet, integration by tables. So integration by tables, again, review of section 2 right here. Integration by tables ends up getting us this answer, and normally there'd be a plus c in our answer, right? But since this is like a definite integral, you know, you don't do a plus c when you have limits of integration. And so there's our answer. So we made it a limit, obviously, but we've already integrated with tables. And so after this comes time to plug in your limits of integration and subtract them. So this is plugging in b, this is plugging in 1, and we're subtracting those quantities. So all these uses of parentheses that you're seeing, quite necessary, so quite important. So I guess I have no answer written except for down here. Like that is the final answer down there, but letting b approach infinity. So again, if this b approaches infinity, then e to the negative b, that's going to be approaching 0, right? So all this approaches 0. Same thing here. All this approaches 0 if b approaches positive infinity. E to the negative that will approach 0. So over here, when this negative distributes, and we have basically like positive 1 over e, because remember, e to the negative 1 is just 1 over e to the positive 1. So we have like 1 over e, and again this distributes, so plus 1 over e, and that's where we end up with like a final answer of 2 over e. So that converges. And again, these directions are probably the bestest directions. Evaluate it, or just state that it diverges, you know. So that's the answer. And I'm not quite sure what's behind. Was it just some other algebraic way to play with this? Okay, factoring. So this was just like another different path you could have went down. Again, it's not really necessary. I'll just move all these boxes, and if you want to look through that. But again, the final answer, no matter what, is 2 over e. I think this is the last example, pretty sure. So again, we're going from negative infinity to infinity. So we're going to be, remember, how do we handle this? How do we handle when it's negative infinity to positive infinity? Well, that's going to get broken up, and we're going to pretty much always use 0 because it doesn't really matter. So we're going to break it up and go from negative infinity to 0, and then the other integral is going to pick up where it left off and go 0 to positive infinity. Okay, and I just kind of rewrote this as 1 plus x squared. I rewrote it as, instead of dx over all that, I just put the dx over here and 1 over 1 plus x squared. So now it's actually time to integrate. This is, and again, this is also going to be a limit, right? So I'm assuming on the next step I made it into a limit, and going from what? A to 0, and then 0 to b, and then letting those approach negative infinity and positive. So it's going to become a limit, right? But we also have to integrate sooner than later. So how do we integrate 1 over 1 plus x squared? What do we do to actually integrate that? What is the integral of 1 all over 1 plus x squared? Maybe right now you're thinking through all your different techniques of u substitution and integration by parts and partial fractions, and you're just trying to rack your brain. Spoiler alert. Pause it now if you don't want a spoiler. But spoiler alert, this is actually one of those special ones that you're going to have to find on your reference sheet. So if you look at your special little reference sheet of kind of special integrals, you'll find it on there. Okay, so if you want to, again, pause the video again and take a look at your reference sheet to try to find it on your own, I'll give you, you can pause it right now, but I'm going to be revealing it in 3, 2, 1. So the integral of 1 all over 1 plus x squared is the arctangent, or inverse tangent. So we made it a limit, we integrated, and after this, now we're going to be plugging in those limits. So we plug in 0, we plug in a, subtract them. That's a whole one big thing. And then over here we plug in b, and we plug in 0 and subtract them. And now we look to analyze the limit. So what is the inverse tangent of 0? What is the inverse tangent of 0? Inverse tangent of 0. Well, that's just still 0, okay? And if you let a approach negative infinity, what does the inverse tangent of a approach? I'll let you think about that for a second. How about over here? Like if we let b approach positive infinity, what does the inverse tangent of b approach? And this is obviously just going to be 0, so maybe I can at least reveal that. So how about over here? If b approaches positive infinity, the inverse tangent, you can say, approaches pi over 2. And as a approaches negative infinity, then the inverse tangent actually approaches negative pi over 2. So, yep. And so you put all this together, a minus minus plus that, so you end up getting pi when all this kind of comes together. So the final answer here is pi to this. So so that's improper integrals, right? So again, to summarize, there wasn't a whole lot here, different kinds of stuff happening. It was kind of the same thing all throughout, just kind of, if you're going from some number to infinity or from negative infinity to some number, it was pretty much the same routine, make it into a limit and kind of all that stuff. But anyway, that's that for section 3.5.